Hi folks. In this video we're going to talk about how you calculate the population variance and the sample variance. We're going to start off with the population variance. We're going to be making the heroic assumption that the values that you see in front of you under the X represent the entire population of data. And then we're going to assume that this actually equals a sample, and we're going to do both of those calculations and show you that the population variance and the sample variance are different from each other. And then we're going to go another step and calculate the population standard deviation and the sample standard deviation because, hey, why not, right? The first thing I usually do is I calculate X bar. And remember, X bar is just the mean of the sample. In this case, X bar and mu are calculated exactly the same way because we're just simply calculating the average of all of our X's. Okay, so the population variance is going to assume that X bar here is actually mu. So just simply think of this as both X bar and mu. Now I'm going to spell it out because I don't want to change to symbols in the middle of all of this. Okay, so we've got X bar and mu here. Now what we need to do is if we're doing the population variance, we're going to take X bar and we're going to subtract that from each one of our X's. Okay, and one of the things that we want to do is lock X bar in place. We can do that by putting a $sign in front of the 12. We're going to eventually copy down this formula, and as long as we keep everything going down the line or down this column, then B4 is going to change to B5 and then to B6 and then to B7, but B12 is going to stay B12 for the entire column of functions that we copy down. Okay, so we've got B4 minus B12 here, and then this is X minus mu. So the next thing we need to do is raise this entire quantity to the second power. We're squaring it. Now, where do we get n from? Well, remember that n is your population. It's the number of observations in the population. Little n is your sample size. But we're dealing with big N right now. And so big N is equal to 1, 2, 3, 4, 5, 6, 7. And so N is 7. So we're going to divide this entire thing by 7. And I'm going to put it in parentheses just to be safe. Okay, so the B4 minus B12 raised to the second power, that's X minus mu squared. And we're going to raise that whole thing to the second power. And we're going to divide it by 7. When we enter that, that gives us our very first calculation of this whole piece right here. Now all we need to do is copy it down and sum it up. Because this sigma here, this Greek letter sigma, means that we're going to sum up all those values. And so the sum of X minus mu squared divided by n is equal to 170. So this is our calculated population variance. Now let's go out here and use Excel's built-in function to calculate it and make sure that we did this correctly. So when you're calculating the population variance, you say equal VAR, and you see it brings up multiple functions with the same starting values here, and we're going to use VAR.P, which is the population variance. And then we're just going to put into that B4 to B10, close parentheses, enter, and look at there. Same number. So we've calculated the population variance correctly here. Now let's do the same thing for the sample variance. Well, in order to get the sample variance, the only thing that I need to change in this entire equation is instead of dividing by 7, which is n, I'm going to divide by n minus 1, which is 6. So in this case, I'm going to be copying down 6 all the way until I get to the bottom. And so what that says is that the population variance is 170.245, but the sample variance, if this is a sample rather than the population, is going to be equal to 198.619. And let's make sure that that's correct. So equals VAR, and the VAR.S is the sample variance. And again, we're going to select those same numbers and enter, and again, we got the value correct. Okay, so the population variance is 170.245, the sample variance is 198.619. The only difference we're making here is in assumptions and calculating based on n-1 in the sample variance versus n in the variance. Okay, so why is it n-1? Well, in layman's terms, the reason that we use n-1 is because the sample standard deviation's properties in small sample sizes tends to lead to a biased estimate. And by subtracting off a 1 in the denominator, in the limit, it pushes the sample standard deviation toward the population standard deviation. And so the estimate gets better. So now how do we find the sample standard deviation and population standard deviation? To find the population standard deviation, you just take the square root of the population variance. S equals SQRT. So this is variance, and this is standard deviation. To find the sample standard deviation, we take the square root of the sample variance. And so you can see that the population standard deviation and the population variance tend to be a little bit smaller than the sample standard deviation and the sample variance. And it's because of this n-1 being used rather than n. Usually we have a sample and not a population, and so most of the numbers that we calculate end up being sample statistics, not population parameters. If you type into Excel equals VAR and highlight a column, Excel returns the sample statistic, not the population parameter. And so again, if we were to say equals VAR, open parentheses, and we don't tell it whether it's population or sample, and we select these same numbers, you can see that it gives us the sample statistic. That's something to note. As far as I can tell, every time there's an option to do sample versus population calculations, if you don't decide beforehand and put a .p versus a .s, then it automatically assumes that the thing that you're calculating is a sample statistic. If you have any questions, drop me an email. Talk to you later.